you. And we finished the unit 8 about the op amps, and we'll have a set of examples today to review the circuits and how to analyze or how to determine the closed loop gain for a non-inverting amplifier, inverting amplifier, V out, VF, VZ in, VZ out, and the CMRR. That's the circuit that is an op-amp circuit that is connected as a non-inverting amplifier. You notice that the V in and the V out will be in phase, means that there is no phase shift between the input voltage and the output voltage. In the same time, the other two resistors, the RF and the RI, which will make the feedback network, are connected in series, and a portion of the output voltage, it's returned to the input voltage. Now, suppose that the op-amp has the given data from the specs. The Z-in, I mentioned that usually it's in, mega ohms, can be anywhere between few mega ohms, 1 or 2 mega ohms to 10 mega ohms or greater than that. The Z-out is around, 100 mega ohms, 100 ohms, and the typical value is 75 ohms, and you notice that I used the Z out as 75. The open loop gain, again, it's provided by the manufacturer, and it's given as 10,000, anywhere between few thousand, 10,000, 50,000, and 200,000 value for the open loop gain, and the ACM, the gain for the common mode, as 0.2. I mentioned that the gain for the common mode, it's in term a very low number, can be anywhere between 1 or 0.1, 0.5, and 10. Usually it's in this range. And now let's try to find, those values or characteristics for the non-inverting amplifier. With the given data and the value for the V in, RI, and the RF. Now we are looking to find what is the gain for a closed loop circuit for a non-inverting amplifier. Now, starting with the gain, and I will put it down as the gain for a closed loop. You notice that there is a closed loop, and I'll put in bracket as the non-inverting amplifier, which is equal with 1 plus the RF over the RI. Okay. Now, you notice that the RF, it's 15 divided by 5 kilo ohms. We'll end up with a gain for the non-inverting amplifier as being equal with 4. Knowing the gain for the non-inverting amplifier for the circuit, we can determine what is the output. V out is equal with the gain, ACL, for a non-inverting amplifier, multiplied by the V in. Again, I'm skipping, the values that has to be added, and I will put, just the answers. You notice that the V in is 2 millivolts. The ACL for a non-inverting amplifier for this circuit is it's 4 multiplied by 2 milliamps makes the output voltage as 8 millivolts. Okay, next step. It's finding B. What is the B? It's the attenuation, and we can determine B as being equal with the Ri. That's the Ri over the Ri plus the Rf. You notice that the B is a dimensionless number, and the Ri, we determine that the Ri is 5 divided by 20 makes B equals with 0.25. This is actually, the ratio that the output voltage is returned to the input of the op amp, the voltage that is referred as the VF, as the feedback voltage. You notice that the RF is series with RI, and actually the RF is the voltage across RI. The voltage VF, again, that's a voltage divider. The voltage VF is said that it's a portion, or it's a ratio of the output voltage. It's equal with, or applying the voltage divider rule, is the Ri over the Ri plus the Rf multiplied by the V out. Again, you notice that this ratio of these two resistors, it's 0.25 multiplied by the output voltage, which is 8 millivolts, makes the VF as equal to 2 millivolts. Okay. Now remember that the VF, again, it's the voltage across the Ri, which is the applying the voltage divider rule is the resistance in question divided by the RT. But the RT is the sum of the two resistances, the Ri and the Rf. Okay, now moving on to the impedances. That's the input impedance for a non-inverting amplifier. And I mentioned that in class that the input impedance for a non-inverting amplifier is greater than the input impedance that is provided by the manufacturer, which is the open loop impedance for the amplifier, and equals with bracket 1 plus A OL multiplied by B. And the bracket is multiplied by Z in. Now I'm substituting with numbers. Z in, it's given and it's 2 megohms. AOL is 10,000, and B we determine that is 0.025. 0.025 multiplied by 10,000 makes 2,500 plus 1 makes the input impedance being equal with 5 gigaohms. You notice that if the initial op amp has an input impedance as 2 megohms, being connecting as a non-inverting amplifier, we determine that the input impedance is greater than the input impedance for the non-inverting amplifier. Now, in terms of the Z out, to determine the Z out for a non-inverting amplifier, we have to know the value of the Z out. That's the Z out provided by the manufacturer, or is from the specs, over the 1 plus AOL multiplied by B. And doing the calculations for the Z out is 75. What I'm expecting, a very low value, because 75 ohms is divided by a large number, which is the AOL, the gain for the open loop multiplied by B. We determined that the gain for the open loop multiplied by B is 2500. 75 divided by 25 makes about, let's say, 30 milliamps. Now, you notice that the output voltage is much larger, or it's greater than the input impedance for the non-inverting amplifier. And the Z out is much smaller than the output impedance for the op amp. Now, one more calculations is in terms of the CMRR, common mode rejection ratio, which can be determined as 20 log of AOL, and it's given over the ACL. And once you do the calculations, and is the logarithmic function of the ratio of the two values multiplied by 20 makes about 23.98. I will approximate that as the 94 decibels. You notice that, based on, the given data, that's, the given data, again, that's the data that is provided by the manufacturer, having the input voltage as 2 millivolts, the two resistances, Ri and the Rf. We determine all the other quantities that is the basic calculations for a circuit, an op amp that has the feedback network. Now, moving on the second example. Now, the first example was in terms of the non-inverting amplifier. There is a particular case, and I will put it on this side. Suppose that I'll say if the RF is 0 ohms and the Ri equals infinite value. Means that I will convert this circuit for a non-inverting amplifier as a voltage follower. The abbreviation for the voltage follower is the VF. Sometimes you will see this notation, the VF as a voltage follower. Now, going back to these calculations, I said that a voltage follower is a particular case of the non-inverting amplifier. Now, what is going to happen with the gain? You notice that the RF is 0 divided by any number becomes 0, means that the gain for a closed loop for a voltage follower is equal to 1. In the same time, making to calculate the output, what will be the output? The V out is the gain, which is equal to 1 multiplied by V in, means that the V out will be the same with the V in. Means that there is no gain for a voltage follower, or we can look for a voltage follower as a non-inverting amplifier with a gain of 1. Now, what will be the other changes in terms of the calculations? All the calculations stay the same because, again, it's just replacing the Ri with infinite and the Rf with 0. Means that in the VF or the Z in, Z out, I'm replacing B with 1. make sure that you follow, the same steps and the same equations for a voltage follower as a non-inverting, or a particular case of a non-inverting amplifier. Means that in this example, if I'll make, B equal, or I'll make, B equal to 1, because B becomes 1. It's the Ri, which is infinite, divided by infinite, makes, the B equals 1. Or replacing B equal to 1, I will determine what is the input impedance for the voltage follower, which I'm expecting, a larger value than, 5 gigaohms. Why it's a larger value? You notice that this example, or, this equation has the open loop gain multiplied by Zin, making, B equals to 1, the bracket becomes a larger value multiplied by Zin, which will make, a larger value for the input impedance for a voltage follower. In the same way, we can look, in, this equation for the Z out. You notice that, again, I will make, B equals 1, and I will calculate the Z out, and I'm expecting the Z out being smaller than 3 milliohms. The CMRR stays the same because the voltage followed does not affect the CMRR, which has, the ratio of the two gains, the open loop gain and the common mode gain. Means that we can look, for or another circuit that derives from the non-inverting amplifier. It's a voltage follower, and we discuss, what is going to happen and what will be the changes in the calculations if the circuit is converted, or it's a voltage follower. Moving on, the second circuit, which is, I may ask, what type of circuit is this? What type of circuit is this? Now let's have a look on the two inputs. You notice that the non-inverting input is connected to the ground, and the inverting input receives the input voltage, and in the same time the RF, or the feedback resistance, is connected between the output and the input. Remember that we talk about the zero virtual ground on the inverting input. That virtual ground, again, is due to a very large impedance between the two inputs of the op amps, which makes the potential of the inverting input as 0, and we are taking, this consideration into analyzing the circuit. We may look for, the same quantities in terms of the gain. That's the gain for a closed loop for an inverting amplifier, the V out. In the same time, we are looking for the two currents. Now, if the resistance Ri is connected to a virtual ground, there is a current that flows through it, and I will label that as the I in. Now, the output voltage, or the output of the op amp, is connected through RF to through resistance RF, which will make, the IF. Here we go. Now we can calculate, the input current, the feedback current, which is the current that flows to the Ri, and the current that flows to the RF. Now I use, the same data. That's why I just, copy, to stay consistent with the input voltage, the Ri, RF. And I'm assuming, the circuit has the same data, the same, given, or the input value for the problem, Z in, 2 megohms, Z out 75 ohms, and our AOL, the gain for an open loop 10,000 and the ACM 0.2. Now, the only change in the first step is finding the gain for the closed loop. The gain closed loop for an inverting amplifier. You notice that is an inverting amplifier. Why it's an inverting amplifier? The signal actually is connected to the inverting input of the op amp, means that the phase shift between the output voltage and the input voltage is equal with 180 degrees, means that always I have to have that phase shift in the equation that it will define the closed loop gain as a negative. You notice that is a negative RF over the RI. RF is 15 divided by 5 makes a gain of 3. Okay, in the same way we can look for finding the output voltage. The output voltage is the gain closed loop for an inverting amplifier multiplied by the Vin. Vin is 2 millivolts and the gain is 3, makes an output voltage, and again it's negative 6 millivolts. What's the meaning of that negative sign, which is very important for an inverting amplifier? That negative sign shows that the input voltage is amplified with a gain of 3, and in top of that there is the phase shift between the input and the output. Means that if the input is positive, the output will be negative. If the input is negative, the output will be positive. Is in the same way that we did in lab, we did in multisim, finding or determining the phase shift between the input and the output for an inverting amplifier or a non-inverting amplifier. Now, next step is how can we determine what is the input current? Again, the input current, let's have a look on this circuit. I mentioned that the RI, or the input resistance, is connected between the input voltage and the virtual ground. Means that I can find the input current as the ratio of, or applying the Ohm's law, the ratio of the Vin over the RI, which makes a very small current as the 0.4, those are microamps, which is about 400 nanoamps. You notice that is a very small current that flows through the input of the op amp. In the same way, we can look, or we can find what is the current that flows through the RF. It's the output voltage. That's the V out. That's the V out divided by the RF, and we'll determine that the current is the same as 400 nanoamps. The two currents, the input current and the feedback current, are the same. In terms of the Zin, that's the Zin for the inverting amplifier, and I mentioned that in class. You notice that the input voltage, or what the input voltage are seeing looking into the circuit, and the RI is connected to a virtual ground. The Zin, it's almost the same. That's why I'll put the approximation that we can look for the Zin for an inverting amplifier as being equal with RI. There are no calculations required in terms of the Zin, which is 5 kilo ohms. Okay. Now, next step is finding what is the Z out. Now, to determine the Z out, has the same equation or the same formula as an inverting or a non-inverting amplifier. That's, the Z out provided by the manufacturer over 1 plus open loop multiplied by B. Okay. If there is, the same equation, what do we expect? To have, exactly the same value as 30 milliamps. Okay. Now let's try to determine B, and I'll put it aside that B in the same way we can look as the Ri over the Ri plus the Rf. Now I'll put that in bracket, but there is no require, to redo the calculations because we are using, the same numbers as in previous example. Now, in terms of the CMRR, common mode rejection ratio, the same equation, 20 log of AOL divided by the ACM. And what do we expect? Exactly, the same value, 94 decibel for the the CMRR. Next step is, and that's why I make it in this way, because now we can alter, we can change, the inverting amplifier, and based on, these basic calculations, we can have the summing amplifier. You notice that that's, a small alteration or a small change that we can make in the basic of the inverting amplifier, and now we are converting, the main circuit into a summing amplifier. Now, the assumption that we have to make a summing amplifier, and I'm using, two inputs. The Ri, it's labeled as the R1 because now I have multiple input voltages. And I will try to relate, the input voltage or the input resistance for the input voltage V in 1 as the R1. In the same way, I will label, the input resistance for the second input voltage as the R2. Another assumption that we have to make is the RF being equal to the R1, R2, which is, the same with the Ri. That's a unity gain. If I'm looking back in the equations for the gain, you notice that, again, the gain for a closed loop for an inverting amplifier, it's, again, I'll put that in bracket, is the RF over the Ri. You notice that the RF being equal to Ri makes, the gain of 1. We are calling, the unity gain because there is no amplification or no gain between the input voltage and the output voltage. What the circuit does, it will have, the addition between the V1 and the V2. Means that in order to determine the output voltage, again, it's a negative of RF over Ri, but we determine that the RF over Ri is equal to 1 because it's a unity gain. Okay? Now, RF over Ri. I'll write it down in this way. And we have the addition between the two inputs. And we have the V in 1 plus the V in 2. Suppose that we have 3 or 4 or 5 inputs. It's the addition between the two inputs. Again, the ratio of the Ri over RF over Ri is equal to 1, means that the gain is equal to 1. Now let's substitute with given values. Okay, now we have the 2 millivolts plus minus 5 millivolts, which makes, you know, minus 3. Minus 3 multiplied by the negative sign in front of the on the bracket makes the output voltage as 3 millivolts. Again, the bracket is minus 3, but in top of that we have the negative sign in front of the bracket, which makes the output voltage as 3 millivolts. Another small alteration of this circuit. Suppose that, and I mentioned, if there is a unity gain, all the resistors has the same values. Most of the time you will see, you know, in kilo ohms range, you know, few kilo ohms, you know, or few tenths of kilo ohms. Again, is not critical, but I'm not using, you know, few ohms because the current will be too large, and the limitation of the output current for an op amp is limited to 20 milliamps. Remember that. That's why, you know, the R1, R2, RF, Ri, you know, it's in terms of few tenths of kilo ohms. Now, suppose that I'm having, you know, a summing amplifier and I would like, you know, to have a gain. Suppose that I'm choosing, you know, to have a gain greater than 1. What is going to happen? Suppose that, again, I'm making the assumption that the closed loop gain for an inverting amplifier, that's the inverting amplifier, greater than 1. What that means, I'm using, you know, the RF as the same value, and I'm using, you know, the resistance R1, resistance R2 as being equal with 5 kilo ohms. Okay. Now let's do, you know, the same thing, the same way. We are looking to determine what is the output voltage. Again, I'll write the equation negative of the RF over the RI multiplied by the V in 1 plus the V in 2. Okay. Now we determine that, you know, the bracket is minus 3, and the RF over RI, that's 15 over 5, which makes the gain of 3, means that RF RI, that's, you know, the gain, and is equal to 3 multiplied by minus 3 makes, you know, minus 9 multiplied by the negative sign makes an output voltage as 9 millivolts. You notice that the only change is the 2 or 3 resistances on the circuit by simply choosing, you know, the R1, R2 having, you know, the same values, and the RF greater than the R1 and or the R2. Now, an averager. Now, suppose that we want to make, you know, the average of the 2 input voltages. Means that I'm looking again in this equation. Means that I'm having, you know, 2 inputs. Means that I have to divide the sum of the 2 inputs by 2. What that means that the ratio of the RF over the resistance R. Now let's talk, you know, about the resistance R, and I will label the R1 being equal with R2 with the resistance R. Means that I have to make the ratio of the RF over the resistance R as 1 over N, and I have to replace N with 2. Why? Again, we have, you know, the 2 inputs. Means that I'm having, you know, the sum of the 2 input voltages divided by 2. Okay. With this assumption, if we are keeping, you know, the same feedback resistance, RF as 15, and the R1 is the same or is equal with R2 and is equal with the resistance R, having, you know, those 2 conditions, the R1 equals R2 and makes, you know, the value of 30 kilo ohms. Now, let's write again the same equation, negative RF over the resistance R or the RI multiplied by V in 1 plus the V in 2. Now, the sum of the two input voltages has to be divided by 2. Means that the RF15, the R, it's 30. Means that I will end up having, this ratio as 1 over 2, which is, 0.5 multiplied by the difference between the two voltages. And in the previous equation, the sum of the two voltages is minus 3. Minus 3, I'll put that, millivolts. That's minus 3 millivolts. Half of 3, it's 1.5. And you notice that the output voltage becomes 1.5 millivolts. That's an averager. Suppose that I'm having, 3 inputs. What should I do? I have to make, the ratio of the RF over the R, or the resistance R being the R1 equals R2 equals R3, as being equal with 1 over 3. Means that I have to choose, the resistance R1, 2, and 3 as 45 kilo ohms in this example, which will make, the output voltage as 1 millivolt, being the average of the 3 voltages. Suppose that, again, the bracket stays, the same for the 3 input voltages. The output voltages will be divided by 3, having, 3 input voltages. Another type of the circuit, or, another specific application for an inverting amplifier. It's having a different weight on the V1. I'm making an assumption that I want to put a weight on the V1 as 3 and the weight on the V in 2 as 2. Now I'm writing, the same equation, except that I will multiply the RF over R1 with the V in 1, RF over the R2 multiplied by V in 2. Okay, now let's try to use, a different color, because I'm showing, what we want. Again, what we want to put a different weight. What means a different weight? A different gain for the V in 1 means that I have to make, the ratio of the RF over the R1 as 3. That's, the weight on V in 1. And the weight on, or the gain on the second input voltage, I'll make it 2. Okay. Now let's have a look on, this approach, which is, very simple. Now, suppose that I'm using, the same RF. Once you know the RF value, or we can choose, the RF value, the weight or the gain for the input one being equal with 3 means that I can write, the 3 as being equal, which is the RF, as the RF over the R1. Okay, notice that the RF is 15, right? The R1 will be 15, or the value of the RF divided by 3, which makes the R1 as being equal with 5 kilo ohms. Now, the same way, or the same approach for the input 2. Suppose that, again, the weight for the input 2 is equal to 2. What that means, the RF over the R2 has to be equal with 2. RF is the same 15, which makes the resistance R2 as being equal with 7.5 kilo ohms. Here you go. Now I'm rewriting the equation using the weight for the input 1, input 2, and I'm substituting with these values. Sorry, it's negative 3. That's the weight for the V1, V in 1 plus 2. V in 2. Now trying to substitute, the values. How we can write that? It's negative, that's, 15 kilo ohms over, I say, 5 kilo ohms multiplied by the V in 1. Second one is, because it's 2, we determine that it's 7.5. That's 15 kilo ohms divided by 7.5 kilo ohms multiplied by V in 2. Now, in this equation, I will substitute the value of the V in 1, which is 2, that's, 2 millivolts. I'll put that in bracket here. The V in 2 was negative 5 millivolts. Now let's have a look on the calculations. Again, I'm just showing, that's why I put in bracket here. I'm just showing, from where it's coming, this weight, the RF over R1 multiplied by V in 1, RF over the R2 multiplied by V in 2, is that I'm putting, different weight or different gain or different amplification ratio for different inputs. Now that's 6 millivolts, and the 2 times, that's negative 10, which makes negative 4, and the negative sign in front of it makes, the output voltage as 4 millivolts. And that's, the answer for the problem. Again, suppose that I'm having, just two inputs. Now we can extend that, having, 3, 4, 5 inputs, and having, different weight or different gains for each individual input. Now we cover, most of the problems that we are using, in assignments and in tests. Some other problems which are, very simple, just one-step calculation in finding the resistance for the instrumentation amplifier, or finding in the output voltage, or finding the value of the input, and or based on the input voltage, finding the output voltage for an integrator and or differentiator. Any questions, comments, concerns, please? Those examples, again, helps you for the assignment. It will be posted on D2L bit later today. I have to brush it up, I have to clean it up a little bit, and it will be posted on D2L today or tomorrow morning. Any questions, comments, concerns, please? If you don't have any questions, have a nice day, guys. Thank you.